Hi, welcome to Algebra 2 Common Core. Today we're going to continue our work with graphs of sines and cosine functions by looking at how we can model real-life situations. Very often we can use both sine and cosine functions to model real-world phenomena, especially phenomena that is periodic or that repeats in cycles. Now let's go back to our original equations for sine and cosine graphs. We want to identify what each part of that equation represents. We've been working on this whole week on making graphs and looking at how the coefficients affect those graphs. So you may have to take a few minutes to pause the video and write down what each thing stands for, and then we're going to draw a diagram. So the first two variables generally go together. The A is always my coefficient for sine and cosine. A stands for amplitude. Now remember that the amplitude is always the positive number in front of the sine or cosine. If there is a negative number in front of the sine or cosine, then that just tells me that my graph goes down first instead of up. So the amplitude is the distance that the curve rises or falls above the midline. D is going to be that midline on the graph, or what the average value is. So on my graph, I'm going to go ahead and put that midline on. And I'm going to call that value the D value. So when we look at our graph, we should be able to tell that the amplitude is that height above or below the midline. So it's going to be this distance right here. That's my amplitude. So I'm going to mark that one A. And it's always going to be the distance from the midline, from the blue, up to a peak or down to a valley. The A and the D values are vertical distances. So whether I've shifted my graph up or down, that's represented in D, and then how much the graph goes up or down from that midline is going to be my A value. So always think of the A and the D as vertical quantities. Now the next parts, C, B, and P, those are all horizontal distances. So first of all, C. If you notice in your parentheses with the X, I can either add or subtract a C value. C is going to be the horizontal shift. So I'm going to shift the graph to the right or to the left based on my C value. B is going to be the frequency of the curve. Remember that we always say that when we know the frequency and we know the period, then B the frequency times P the period always has to have a product of 2 pi. And that's going to help us in our application problems as well. P stands for the period of the curve. That means the width of one cycle of my curve. So going back up to my picture here, I'm going to say that the P value, that period, the width of one curve, is going to be shown on my graph by going from a spot on my graph. So for example, if I'm going from peak to peak, that distance right there is going to be the P value, the period, the width of one cycle. So now let's go ahead and take a look at some application problems. In example number 1, we're talking about tides in a particular bay. Very often water, like tides or waves, can be modeled by trigonometric functions. So we're going to use a cosine curve. You'll notice that I've left off the C in this cosine curve because I'm not going to talk about any horizontal shifts this time. T represents the number of hours since high tide, and Y represents the depth of water in the bay. So the maximum depth of water is going to be 36 feet. So we're going to take a look at that and say, okay, I know my maximum. I also know the minimum is 22 feet, and that high tide hits every 12 hours. So it's going to help us to start with a sketch. So in part A it says on the axes, sketch a graph of this scenario for 2 full periods. So first of all, notice that I've labeled my x-axis by 6s, all the way up to 24 because I want to make it through 2 full periods, and each period is 12 hours. Then it says let's label the points on this curve that represent high tide and low tide. So we know, of course, that our high tide is 36 feet. Since it says that our time is number of hours since high tide, that means that at time 0, I've got to have a high tide. So I'm going to start with a dot at 0, 36. So I'm going to start with my peak right there. Now you'll notice that I'm going to be back up to a peak at 12 hours because it says that it hits high tide every 12 hours. So that means again at 12 I'm going to be at 36, and again at 24 we're going to be at a height of 36. Now I've got to hit the minimum depth, which is 22 feet, and that has to happen halfway in between. So after 6 hours, I should be at 22 feet, and between 12 and 24, halfway is 18, so again we'll see a height of 22 feet at that point. So I can go ahead and connect those points, making my curve. You'll notice that this is a cosine curve because I'm starting at the amplitude and then I'm going down to the midpoint. So we could calculate what our midpoint is by looking at our high point and our low point. So that's the first thing that I'm going to do in part B. I'm going to say let's find that midline. So to find the midline or midpoint, that's going to be my D value. And we know that the highest is 36, the lowest is 22. So one way of doing this, consider it an average value. Let's find the average of the heights. So 22 plus 36 divided by 2. When I do that calculation, I'm getting an answer of 29. So on my graph, I can put that on there as, I'm going to make it a dotted line at 29. And I see that that makes sense. I do definitely have half of the graph above and half below. And that's going to be my D. Now my A will be the amplitude, so that's how far it is to go from the midline to a high point or from the midline to a low point. So I can do a subtraction either way. I can say my high point was 36, and if I subtract the midline, 36 minus 29 is giving me a value of 7. We all know that the p-value is the period, how long it takes for one complete cycle, and it said in the problem that that was going to be 12 hours. And to finish it off, let's do our b value. We remember that p times b has to equal 2 pi. So if I already know that p is 12, I can calculate b by dividing both sides of the equation by 12. So b will be equal to 2 pi divided by 12. So b would be equal to pi over 6. So let's go ahead and put all of this information together to create our equation. So we will say y is equal to the a, which in this case amplitude is 7, multiplied by the cosine of b, which in this case we've calculated b to be pi over 6, times t, because I'm multiplying by my time. I'm going to put that quantity in parentheses, and then add on the d value that we calculated, which is 29. We could test this in our calculator and make sure that we get a graph. Again, make sure you're in radian mode and make sure that your x-axis is going to go from 0 to 24 and your y-axis has to go from 0 to about 40, and I counted by 5s. Now for the last part of this question, it says that tanker boats cannot be in the bay when the depth of water is less than or equal to 25 feet. It's just not deep enough. So we want to set up an inequality and solve it graphically to find all points in time on the interval from 0 to 24 when tankers cannot be in the bay. And it says to round our answers 4 times to the nearest tenth of an hour. So you'll notice that I've added a line to my graph, at at y is equal to 25. Now, I'm going to go ahead and put this into my graphing calculator. And again, I expected you to have already put the blue one into your graphing calculator. So let's add the red one by putting in the line y equals 25. We want to know the intersection points for the red line and the blue line, because if the water is below the red line, we know the tanker cannot be in the bay. So take a few minutes and set up your axes. Make sure that your numbers are big enough, your window is big enough to see this complete graph, and then find the intersection points. So I have labeled the 4 intersection points, and I see that the red graph and the blue graph intersect at t equals 4.2, t equals 7.8, t equals 16.2, and t equals 19.8. Now it says, let's determine when the tankers cannot be in the bay. So we of course know that the tanker cannot be in the bay between these two times and between these two times, because in both of those cases the water is just too low. So I'm going to set up an interval and say from 4.2 to 7.8 the tanker can't be in the bay, and then again the tanker can't be in the bay from 16.2 to 19.8. So we could solve that problem graphically, and that's the only way that we're going to be expected to do that kind of problem. Let's look at example number 2. We're talking about the height of a yo-yo above the ground, and we're going to use a cosine function. H equals 1.75 cosine of pi t plus 2.25. H represents the height of the yo-yo in feet above the ground, and t represents the time in seconds since the yo-yo is first dropped from its maximum height. So the first part of the question says, let's determine the maximum and minimum heights that the yo-yo reaches above the ground. Show the calculations that lead to your answers. I drew a sketch of this one and then labeled the sketch so that I could see where the max and min were occurring. So see if you can draw a sketch of what's going on. We have a cosine curve, and we know that t is time in seconds since the yo-yo was first dropped, so my height is going to start at the highest value for the yo-yo. Now let's go ahead and analyze this together so that we can evaluate these heights. First of all, in my equation, I see that my midline, my d value, is going to be 2.25. So I'm going to draw in that average value or mid value. Now on my y-axis, I've labeled by ones. So 1, 2, 2.25 is going to put me right about here. So to find the maximum, we're going to have to take our d, which is our vertical shift, or it's going to be equal to our average value of this function, that red line, and we're going to have to add the amplitude. So we're going to have to say 2.25 is going to be that vertical shift, add on the amplitude 1.75, and that tells me that the maximum height for this graph is going to be 4 feet. Now doing the minimum, we're just going to say let's take that d value and let's subtract the a. So that's going to bring me down to a valley in the graph. 2.25 minus 1.75, and that's giving me an answer of 0.5 feet. So I've pretty accurately sketched this, going from a maximum of 4 down to a minimum of 0.5. The calculations that would be necessary to show are the ones that I've just put here. In part B, it says, how much time does it take for the yo-yo to return to the maximum height for the first time? So we are, of course, going to use our formula. We need to know the period of the graph. So to find the period, we know the property that period times frequency is equal to 2 pi. So therefore, we are going to say that the b value is, of course, the coefficient of t. So I'm going to use for my b the pi because that's the coefficient of t. So now make the equation. So p times pi is equal to 2 pi. Dividing both sides by pi, I get that p is equal to 2. Well, p should be represented in seconds because it's a horizontal distance or an amount of time. In example number 3, we see the example of a Ferris wheel. A Ferris wheel is very often used to represent periodic motion because you can think about the movement of the cars in the Ferris wheel, how they go up to the maximum height, then back down to the ground level, and then back up to maximum height again, and so forth as we go around the Ferris wheel. A Ferris wheel is constructed such that a person gets on the wheel at its lowest point. That makes sense. We're going to get on the wheel at ground point. It says that that point is going to be 5 feet above the ground. So my lowest value is going to be 5. So I'm going to start with my height of 5, and I know that that's where my starting point is. It reaches its highest point at 130 feet above the ground. So that's quite a distance there. So I'm going to go from 5 feet to 130 feet. Drawing this in, I'm getting a graph that looks something like this. Now what I'd like to do is figure out what this equation is and find my A, B, and C. Let's start with the A value. So to calculate the A, actually let's start with D instead. For the D value, I know that I want to find my midpoint between the 5 and the 130. Again, that's going to be my average value. So I'm going to say the midline is going to be equal to D. So I'm going to have to take my low point of 5, my high point of 130, and find the average. So when I do that, that's giving me 67.5 feet. So on my graph, I'm going to make the midline halfway between, and that's going to be 67.5. Now it makes more sense to go ahead and find my A value, A for amplitude, because now I know that if I'm at a high of 130, then the amplitude is just going to be the difference between 130 and 67.5. Now again, there are several ways to calculate this, but this is probably the most straightforward calculation for A. So we're going to say 62.5. Another option for A would be to say, if I know my highest point is 130, and I know my lowest point is 5, if I take the difference and divide it by 2, half of that distance has to be above the midline and half has to be below. So this is also giving me an answer of 62.5. So you can calculate your A in either manner. The last thing we want to take a look at is our frequency and the period. So we know, of course, that it takes 8 minutes to go completely around just one time. So that's going to tell us that our P value is equal to 8 minutes. We need B for our equation, so we're going to say P times B is equal to 2 pi. 8 times B is equal to 2 pi, so solve for B. Dividing both sides by 8, I get pi over 4. So the final equation for this Ferris wheel is going to be y is equal to, now be careful here, 62.5 is going to be the amplitude, but I see from my graph that I'm actually starting on the low part of my cosine graph, so that's telling me that I have to start with a negative 62.5. Multiply by cosine, put the B value, pi over 4, in front of time, and then go ahead and add on your vertical shift or your midline, 67.5. Again, you could test this in your graphing calculator, but make sure that you adjust your window in your calculator. I know that it took me 8 minutes to go completely around, so halfway is going to be 4 minutes. In our last two examples, let's use some of the information that we've learned from the previous examples to solve the multiple choice problems and to figure out some of the missing values. So for example number 4, it says the possible hours of daylight in a given day is a function of the day of the year. So the further we are away from the winter, the longer the days get. The closer we are at approaching winter, the shorter the days are. It's a periodic function because this pattern keeps repeating. In Poughkeepsie, New York, the minimum hours of daylight is equal to 9 hours. That happens on the winter solstice. So the minimum is equal to 9 hours. The maximum hours, and that's the summer solstice, that's equal to 15. If the hours of daylight can be modeled using a sinusoidal equation, what is the equation's amplitude? So let's take a look at our amplitude value. We've got two options here. We can first of all find the d value. That's an easy way to approach it. So we could say that d is just equal to the average of the high and the low. So 9 plus 15 divided by 2 tells me that the d value is equal to 12. That makes sense. So we would have half daylight and half nighttime. Now, to find the a, though, what we're going to have to do is say, let's take our maximum is 15, and let's subtract that d value of 12, so that tells me that the a value would be equal to 3. So I'm choosing choice number 3. I've got one other option to do this problem. I could solve for a also by saying, take the maximum 15 minus the minimum 9, divide it by 2, and that also gives me an answer of 3. So whichever way makes more sense to you, go ahead and use that method. Now let's go to example number 5. We've got another Ferris wheel problem. This one is the actual Ferris wheel at Navy Pier in Chicago. Maybe some of you have been there. It takes 7 minutes to make one full rotation. So if I know that it takes 7 minutes to make one full rotation, then that, of course, is telling me my p value. So p is equal to 7 minutes. The height is going to be modeled by the equation given here, so we'll look at what's missing in that equation. So first of all, let's calculate b. So we know that p times b has to equal 2 pi. We already know that p is 7, so 7 times b has to equal 2 pi. To solve for b, we're going to divide by 7, so b is equal to 2 pi divided by 7. So let's put a box around that. We've shown our work, and that's our answer for the frequency. Now, using this h of t for one full rotation, this car's minimum height is going to be. So we're looking now for the minimum. So let's take a look at the information that we know from our equation. We've got that the amplitude is equal to 70. We've got now that the b is equal to 2 pi over 7. We know that the horizontal shift c is equal to 1.75. And the last thing, we know that the d value is equal to 80. That's our shift. So if we know that the amplitude is equal to 70, but the midline is 80, then what that tells us is that to find the minimum value, we're going to say take my d and subtract a. Take the midline and subtract the amplitude. So 80 minus 70 is telling me that the lowest point on this graph is going to occur at 10. So the minimum height in this calculation will be equal to 10 feet. And again, that's an answer that makes sense because we know how Ferris wheels look. Thanks very much for working tonight on applications, modeling sinusoidal problems. We'll be working some more with this at the end of the week. Thanks. Have a great night. Bye-bye.